Hi guys, welcome to our video lecture for, we would call this an ocean introduction. So we spent a lot of time talking about, there we go. And copy this down as I talk. We spent a lot of time talking about freshwater systems like rivers and wetlands and lakes and kind of the different parts of a river and how wetlands are helpful. And that's been fun, but we are missing the majority of our water. If we remember all the way back to our first lessons on the water cycle, we learned that the majority of the water that we have on Earth is actually salt water. So we're going to spend the rest of our hydrosphere kind of general lessons talking about the ocean, how it moves, what is it made of, and how do we humans use it, and then later we'll learn how we abuse it. But we're just talking about general ocean things today. Here's your vocab. I hope you've either paused me or written this down. And here's your bell ringer. So I would like you to predict for today's bell ringer which picture will have a higher porosity. And give me like a one sentence, remember sentence has a capital letter and a period, of why you are choosing that one as having the higher porosity. Pause this and then we'll move on. So what we'll find out is that A actually has the higher porosity because of the large spaces in between we can think of those as molecules, so let's just call them rocks. So because of the spaces in between the rocks, or the white space, that's better able for gases, but specifically water, to flow through. And B has a lower porosity because it has the small spaces, and it's actually because we have the mixing of large particles and small particles that we get that lower porosity. Those small soil particles or rock particles actually almost act as corks, making it really hard for the water to flow easily through those large blue molecules. Fantastic. Let's move on. That was just a review. So like I said, today, that's for our lab. Today's lecture is about temperature, salinity, and acidification, or that's where we're going to go in the next 2 days. Today we're going to focus in on salinity and a little bit of acidification. So we're skipping this first slide, and I want you to go into your notes where it says salinity. We're starting right there. So here's a question for you. What is in ocean water? Do you know? You'd be surprised because only 96.5% of the ocean is actually our water molecules, or H2O, right? Two hydrogens bonded to one oxygen molecule. The remaining 3.5% actually consists of dissolved gases and solids such as salts. Now, before we get too far with our salt talk, dissolved gases, we have carbon dioxide dissolved into the ocean. There are oxygen molecules dissolved into the ocean. Otherwise, how would our fish breathe? And I'm not 100% sure. I'm pretty sure that there's nitrogen also dissolved into the ocean water. So there are some gases, but we're not really going to talk about those today. We'll talk about only oxygen just very briefly when we talk about upwelling and how we take the oxygen away from the water, but that's in another unit. So we talked about gases. Let's talk about those solids for a second. Salt, normally when we think of it, we think of the NaCl, sodium chloride, and that's the main salt in the ocean. But I want to clear up a misconception for you and tell you that not all salts are NaCl. Salts can be pretty much any of the lower atomic number metals on if you're looking at it, it's the left side of the periodic table, combined with what I believe are called halogens. So chlorine is one, fluorine is another one. So we can have a combination of elements that make what we group into salts. Okay. Here is just a general breakup of those dissolved salts. So if we have a total of 1,000 grams of ocean water, 96.5 or 965 grams of that water would actually be hydrogen and oxygen molecules. That's what this graph is taking us to kind of discover that if we go by the percentages that we have here, 35 grams would be dissolved salts, and if you break that even further into the individual elements, you see that For the most part, you've got that NaCl bond right there. There's over half of it is chlorine. The other big chunk of it is sodium. And then we have trace amounts of magnesium, sulfur, calcium, potassium, and less than 1% of what we call others. So we are seeing that the NaCl is the majority of what we've got in the ocean, but we do have others as well, as evident by that sulfur, calcium, potassium, magnesium, and what we called others. Salinity. So salinity is the amount of dissolved solids, mainly salts, present in the ocean water. Our average salinity of ocean water is about 35 parts per 1,000. And what that means that there is 50 million billion tons of salt in our seas because we have a lot of water. That is a huge number, but remember that 75% of our Earth is covered in water, and the majority of that is salt water. So 1,000 grams of salt water consists of 35 grams of dissolved salts. That's just some quick math for you based on the percentages. What that means to me and you is that's why when we get ocean water in our mouth, it tastes salty. Beautiful. So we found this is kind of weird, and a result you might not expect, but portions of salt per 1,000 parts of sea water. So we can actually see general trends in the ocean water. It's not consistent overall. If the equator is right here, so right above and below the equator, we see our highest amounts of salt parts per million. Kind of above and below our equator. And then as we get closer and closer to our poles, we see less and less salt per water. Now, if I gave you a glass of Atlantic Ocean water right from the middle there to taste, and I gave you a glass of water that came right down here from like the Antarctic region, you wouldn't be able to taste the difference in salt. This is something that scientists have found by measuring the seawater, but just know that it's not consistent across all boards. And actually, we're going to talk about why we're seeing this result maybe a little bit later when we talk about climate overall and how our ocean actually moves. Large amounts of evaporation will increase salinity. So that's kind of a clue as to why. Let's put the other one up there. That's kind of a clue as to why we are seeing our saltiest seas right in those middles there. There's also what we call the gyre, the spinning currents happen right around here and here and here and here. So it kind of gets trapped a little, but large amounts of evaporation will increase salinity. So we are evaporating a lot of our water right here in the warmer regions of the Earth. Would you agree that Florida is warmer than the Antarctic? Hopefully. And then, but we also found that large amounts of precipitation, melting ice, and runoff from land will decrease salinity. So it's interesting to see here on this map that near, for the most part, except, country's hard, Brazil, Peru, that's a big guess. Right around here in South America, that's kind of our outlier, and around here. But for the most part, around the continental regions, we are seeing less salt because of that runoff from land. And then right here, as the ice is melting, we are seeing less and less concentrations of salt, which again, we talk about that in parts per 1,000. Okay. So maybe you've thought about this, maybe you haven't, but let's talk about it. How did the oceans become salty? What happened to make them salty? Here it is. So over the history of the Earth, each year, Earth's rivers carried more and more salt into the ocean. The water evaporates, but the salt is left behind in the ocean. So we know our water cycle is cyclic, so the water moves and it doesn't have a clear path. It doesn't always go from the ocean to the air or vice versa. It can flow around in the system, but our water molecules are constantly recycled is the moral of the story. So as those water molecules are rained down onto different areas, they are They bring the salt with them that they erode from the rocks and whatever way. So maybe you put salt on the roads and it ran off into the streams, in which the streams ran into a river, and a river ran into eventually the ocean, and it started again. So the principal source of dissolved salt in the ocean is actually because of the weathering and the erosion of rocks on land. So if we didn't have rain, our ocean wouldn't be salty. So since the oceans were first formed, they have become saltier. Now more salt is being deposited on the ocean floor as the rivers reach a general equilibrium. So I don't know, and you can do this experiment if you would like. I would love for you to do some science at home, but if you get some water and you put like a spoonful of salt, so if you get a glass of water, you put a spoonful of salt in it, mix it around, it's probably going to dissolve. But if you put like the whole salt shaker of salt in your cup, eventually it's going to reach a point where there's no more water molecules to pick up the salt, and it's not going to dissolve. So that's what's going to happen. Eventually our ocean is going to get to a point where it can no longer pick up the salt molecules and dissociate them. It's something we'll talk about in chemistry if you get there. But it reaches a point where it can no longer hold it, just like maybe if you were carrying groceries from the house, there's a certain amount of groceries that you just can't hold anymore. Water molecules are similar as they pick up salt. Let's talk about ocean resources. So as the population becomes larger and larger, we are facing this issue of water availability. We call this potable water. That means water that we are able to either drink or irrigate our crops with or irrigate our animals with. And there's a limited source of that. To try and overcome this issue, which we're going to talk about in our human impacts unit, our next unit, they have created this desalination process, which basically just takes the salt out of salt water. When I was younger than you, I think I was in 6th grade, my social studies teacher had I don't know what to call it, but we used to watch this show called Voyage of the Mimi all the time. And what it was is this kid, for some reason, was on a boat full of like scientists, I think, and they were stranded on an island. And one of the things that they did, because they didn't have any fresh water to drink, they actually came up with a way to take the salt out of the salt water. They boiled the water, and the salt was left behind, because I told you salt doesn't evaporate with the water molecules, only the water molecules go up. And then they put a black thing in a black bag, collected the condensation, so that water vapor cooled it down, and then that dripped into another pan, and so they had fresh water. But this is similar to that. It takes the salt out of the salt water, but it takes a lot of energy to do this, so it's not a very viable solution to the fact that we have limited drinking water and we are polluting the limited drinking water that we already have. But again, we'll talk more about that another day. And the last thing I wanted to talk about, and I might cut myself short here, just because we've been talking a lot. We'll finish it up tomorrow in our other lecture when we talk about temperature. But ocean acidification. So we have big, beautiful oceans, but we're doing something particularly nasty to them. It has to do with the burning of fossil fuels and the carbon dioxide that is released into the air. When we do that, when the air full of carbon dioxide meets the water, it turns into something called carbonic acid, and that acid is brought into the water, and it can actually have very devastating effects on our ocean. So here's ocean acidification. We will probably get through all the writing today with this, but I'm going to explain it some more in our lecture tomorrow. So ocean acidification is an excess of carbon dioxide from the atmosphere makes its way into the oceans. We talked about that. The ocean is what we call a sink for atmospheric carbon dioxide. Now, a sink is like, think about like your kitchen sink. It holds things, right? Like dirty dishes and whatever else you might have that you put in a sink. It holds things. We call sinks in science things that hold elements. And that's a little general, but that's what it is. It holds extra elements for us, kind of. And the ocean is something we call a carbon sink. And I'm looking at my time now, and it looks like I'm about out of time for this recording, so we'll talk more about carbon sinks and ocean acidification and the effects it's having on the environment in our next lecture. Have a great day.